All right, welcome back to Art of Science. It's been a little while since I recorded an episode, mostly pretty busy with teaching, but it's officially summer, and I'm excited to have my grad student Alex Carney to talk about our new paper. And before Alex introduces himself, I kind of wanted to give a backstory of how we first started working together. So the first class I was in charge of teaching here at Dartmouth was Engines 23, Distributed Systems and Fields, which is a really complicated name. At first, I was like, I have no idea what this means. But then I realized it's just solving partial differential equations and really a lot of like math tools that I learned in sort of an applied math class for physics majors at Middlebury that I think has since changed. But so it's a very mathematical subject. Alex was my TA and helped me a lot while I was kind of learning how to teach in the beginning. And I think we kind of bonded over really loving the subject and really jiving with some of the lessons that are embedded in math in the subject. And I think what's beautiful about this story is that I was in industry for a time, and coming back to academia, I think it feels like, oh my God, so you have to teach and do research. And on the one hand, those feel like kind of disconnected, but this is one of those instances where this research is entirely inspired by like my teaching of 23, because I think it forced me to like embed myself in this idea of like state space and system dynamics in a way that I think really helped inspire the research. And Alex, of course, like went ahead and did it all, but we had a lot of conversations about that. So I think that's kind of the context for what I'm at least excited to talk about with Alex. But, these things are very dynamic. So without further ado, Alex, welcome to the podcast.
Hey, thanks a lot for having me here. I'm really excited to be here today. And yeah, so a little bit about myself. So my name's Alex, and I guess for college, I started off at Skidmore College, which is a small liberal arts school in upstate New York. And I remember when I was trying to decide what college to go to, I ended up choosing Skidmore partly for their music program because I've been a pianist my whole life, and Matthias is a musician as well. So
very amateur.
Well, I'm also amateur, but that's been a fun crossover. But Skidmore had a great music program, but also when they were doing their open house, I went and talked to the physics professors that I would have if I went there and studied physics. And all I could think was, wow, I really like these people. I want to be here and I want to do physics. So I show up to Skidmore, and my plan is to be a physics and math double major. And I meet a couple of students the first term that tell me, are you doing the Dartmouth program? And I'm like, what's that? And apparently there are a ton of liberal arts colleges in New England that have this partner program with Dartmouth, because those liberal arts colleges might not have engineering programs of their own, but they have physics, they have math, they have certainly STEM based courses, but they don't have a machine shop or like an electronics lab per se. And so you can do 3 years at your home liberal arts college and 2 years at Dartmouth, and you can graduate from both schools with a degree in liberal arts and physics or math from your home school and a bachelor's of engineering from the Thayer School at Dartmouth, which I think is a really, really cool program because you get 2 first days of college, 2 graduations, 2 friend groups. It's kind of like, and then also 2 first semesters of college where you're trying to adapt to being in a new environment and taking really hard classes. So it's kind of just take all the good, take all the difficult, and do it twice.
And I guess the key is that you do 1 year here, go back, graduate with your class, and then come here and graduate again, which is,
Yeah,
I think it's
exactly.
sweet you get a senior year with your class.
I agree. So some people, you can technically do 3 and then 2. So we have a
Mm.
student in the lab right now who graduated from Skidmore in 3 years and is here for 2 years.
Mm.
And that's Soleil.
Mm.
But I think doing the 2 years at your home school, your junior year at Dartmouth, your senior year at your home school, graduate, and then a 5th year at Dartmouth is just a really cool program. And honestly, if I could go back, I would recommend it to anybody and I would do it again.
Yeah, it's been great. We've been growing that program, and I feel like a lot of people in the lab are from Middlebury, Skidmore, Amherst, a lot of these schools. So I think it's an awesome thing, and I'm a huge, huge proponent of all you dual degrees. Yeah.
So when I got to Dartmouth, I was kind of thrown into the deep end of engineering, and I didn't really know what type of engineering I wanted to do. I kind of said mechanical when I was coming in because that's sort of the first thing that I thought of when I thought of engineering. I'm like, oh, well, engineering, that's having physical objects and combining them together. What I didn't realize is that I could use a lot of what I loved from math and physics back at Skidmore in engineering. And as I started taking more and more classes, I eventually got to Engines 23 when I was a junior. So I think that was before, maybe the first year you were at Dartmouth or maybe a year before.
Yeah.
And I remember loving the class content because it was so mathematical and so physics based, but really, really struggling with it. And I think part of the reason why I was able to teach it better when I got older was because I didn't understand the content immediately. It took me a lot of effort and a lot of time and a lot of practice to distill that knowledge into a format that worked for my brain. And I think going through that translation of how it's presented to you into how it makes sense to me and it took a long time to do that for me.
So it's just a really hard, I think Fourier in particular, and there's a lot of math concepts that you kind of just need time with. And I like our quarter system in some ways, but it goes by so fast. And I think you just need time to sort of marinate with it for a while and like go use it somewhere else.
Yeah. And I also think as time has gone on, Engines 23 has changed a lot. I think they've tried to stuff in linear algebra, differential equations, because I don't even know if those are prerequisite courses. So you have to catch everybody up on those math topics. And then you say, well, now we're going to partial differential equations, Fourier analysis. So if you haven't taken linear algebra or differential equations when you come in, it's kind of a fire hose, if you will, of content in 10 weeks to get through.
Yes, but okay, so because I think even from the very beginning when you were TAing, we were kind of tossing around some of these ideas. So maybe try to unpack, like in very simple terms, what we were so intrigued by in some of these system dynamics.
Yeah. So when I came back for my 5th year, I wanted to TA Engines 23. I talked to Matthias, and we were talking about quantum mechanics and also classical mechanics. And something that really interested us was this concept of, okay, what happens if you take your system that you're studying in Engines 23 and you make one seemingly small change, which is that you no longer have symmetry between all of the energy transfer inside of that system. So, for example, let's say you had a rope that was really long, like a really long string. But let's say that that string was made of different components at each part of the string. So they all have different loss rates. So they each dissipate energy at a different rate. Or let's say, and this might be a little bit hard to imagine, But let's say you had a rope where energy could flow in one direction along the rope, but not in the other. So you've got sort of like a non-reciprocal transmission problem. And for those of you like in electronics or electrical engineering, it's a little bit easier to see it there because there's a lot of non-reciprocal components in electrical engineering, such as diodes and amplifiers, where it's very easy to say energy goes this way, but not the other way. But coming from a mechanical background where you have masses and springs, it's a little bit hard to visualize what would a one directional spring really
Yeah.
look. I guess if
Just
there's
most of physics.
ratchets.
Yeah. And I guess I'll just quickly interject because I think um, coming from a quantum engineering background, sort of all of quantum mechanics is built on these symmetries. And in a lot of the settings, it's all assuming that energy is conserved within your quantum system. I think one of the biggest realizations, and it's a very deep concept and kind of rather annoying, is the fact that you can almost never completely isolate any quantum system from the environment. And as soon as the system is allowed to interact with an environment, which happens like so naturally all the time, that you can have loss of quantum information, which means that energy just flows into the environment and turns into usually heat or something else that you just can't recover. And it's sort of like saying you take the Griffiths, like the intro quantum mechanics class, and everything, there's no loss. Everything is perfectly energy conserving. And like that would be a really nice world to build a quantum computer in, for instance. But that's not the world we live in. And so there are ways to incorporate interactions with the environment with like open quantum systems. And even a lot of that framework is sort of under some very harsh assumptions about like energy always flowing into the environment but never back. And there's basically the world just isn't fully Hermitian, which is to say like this energy conservation and things like that. And it's certainly not so classically. And so maybe you can pick up from here like kind of what we ended up building. And this is part of the stuff you like Juan's project you were involved in, and we've kind of like taken this the whole way. So maybe just like in a very simple term, like explain what we built, because I think another part of this that I wanted to highlight, and I think we made it very clear in this project, is like we did a lot of math, but the original idea is like what actually happens when you try to build these funky dynamical systems, right? And there's a lot, like the proof is in the pudding. I think I'm very much an experimentalist, but I think now hopefully you are as well. And maybe try to unpack like what we built and like why we built that, and what it sort of led us to.
Yeah. So I'll start with kind of the motivation behind these like systems and how you would get to this point, because what I find kind of interesting is that when you go into undergraduate engineering, everybody takes a class called systems. It might be called something different at your school, but everybody learns about Laplace transforms for the first time. And the system that you study is a mass, a spring, and a damper. So you have a lossy oscillator, and you spend the entire class looking at lossy oscillators or lossy resonators in fluid, mechanical, electrical, etc. types of systems. Then you get to Engines 23, which is distributed systems, and you say, okay, now what if you had multiple resonators coupled together, so multiple mass springs, but we suddenly get rid of the dampers. We don't look at the how loss on this entire massive scale works as much. And then that leads you very easily to quantum mechanics, which works with these lossless systems when you're doing intro quantum mechanics. But like you said, we wanted to explore what do all these non-reciprocal interactions or lossy interactions that aren't really covered in a standard undergraduate curriculum and not really covered in a standard first or second or even third course in quantum mechanics, can we build a system that has those dynamics and just see how it differs from what we would expect? So we had some excellent guidance in the machine shop at Dartmouth, and we fabricated these 3D microwave cavities.
Shout out to Joe Poisson.
Yeah, he's an absolute beast. In the early days of the lab, I think that was one of our lifelines. We didn't have anything. I think you brought a cavity with you from wherever you were before, but
yeah, Andrew, they sent us a qubit in a old style cavity, and we tried to make those post cavities, and it was non-trivial because the students didn't have HFSS. Anyway, those were dark days, but very fun for tinkering, and Joe helped us out a lot. So we ended up, getting these mechanically adjustable, reasonably high quality factor things where you could change how coupled it is, you could change the frequency, and then lock things in mechanically, which is, I think, another theme on this project is you want tunability, but then it can become a beast to wrangle in all of those, dial in all the calibrations and stuff. But yeah, go ahead.
So we started with one cavity, and one microwave cavity behaves exactly as a lossy resonator that you would learn in Engines 22. So I felt right at home. My math worked great. Everything made sense to me. You drive the cavity through one port and you read out the transmission through another port, and you get this beautiful peak called a Lorentzian that every engineer looks at and immediately recognizes. So we said, well, we're not going to publish anything new if we're just looking at a traditional lossy resonator. Let's build multiple and see if we could build lattices, which means multiple cavities all combined together in various ways. And the simplest lattice you can do is two cavities. So we originally were building cavities where there would be a single block of aluminum and then two cavities drilled out of that single block and then a hole between the two cavities. And so you had one block of aluminum and two cavities inside. And that was interesting, but then you're kind of at just two masses, two springs, two dampers with the same damping rate. A little bit more interesting than one resonator, but still not super enticing. So then we decided, let's take two cavities and physically separate them. So it's not one block of aluminum anymore. Let's make two identical copies. And let's use wires like SMA cables, coaxial cables to couple them instead. But then we ran into a problem. Those coaxial cables have a lot of loss in them. It's actually kind of funny for microwave transmission. If you try to go just a couple of meters, you're going to lose a lot of your power versus optical transmission. You can go, fiber optic goes across the ocean and they don't really have too much loss there. So it's interesting how the frequencies that you're working at can highly dictate how fast you're going to lose energy. So what we found was we weren't able to get strong enough coupling between the cavities by using these wires.
Which is to say that light can get from one to the other without damping like crazy. Which usually you deal with damping in the cavities themselves.
Yeah.
It's kind of funny to have damping in the... Either you can think of physicists like to think of photon hopping, but yeah, it's just transmission. Exactly.
And to remedy that, we did what any electrical engineer would do. We just added gain. What happens if you just put an amplifier in the middle of that directional coupling between the two cavities? But a amplifier is by definition one directional. It doesn't go in both ways. It also acts as a diode. And so we had to have a symmetric path on the way back that had an amplifier going in the other direction. And for such a seemingly simple system, just two cavities, which are essentially RLC oscillators, with this one change of putting gain not within the cavity itself, but within the coupling between the two cavities, we found some really, really cool dynamics.
And I think that's a new thing, certainly in microwave space, because this sort of like bidirectional gain thing, and this is really like we're going all the way back to sort of Juan's original work. You have to be careful about the phases, because the beautiful thing about these symmetric interactions, like in this single block with two cavities, physics sort of determines that if you have a rate of hopping from one to the other, it has to be the same as the reverse. Physics just conserves those sorts of things. And sort of baked into that as well is that if you have a photon going from one cavity to the other, there's some phase accumulation perhaps in that hopping. Well, then that phase is reciprocated in the way back and everything stays symmetric. Here, like, we have different amplifiers and maybe different cable lengths, certainly different cables. So we had to get the phase balanced. So we added this microwave phase shifter, which is it's useful. I mean, microwaves suck for a lot of reasons for loss in cables, but all this, cell phone telecom stuff, there's all these components that we can just buy. And one of those is a phase shifter. And so I guess that was a key thing, that we could either get sort of a matching condition where like you can tune the rate with gain, and they're nice and symmetric, but then we can just rotate the relative phase and then everything is like purely non-reciprocal. And what did we find other than like, yeah, I mean, what did we find?
What was cool from my perspective was in the original experiment, when we kept all the gain low and nothing kind of too exotic, yeah. I was able to kind of predict what would happen with my math. Mm-hmm. And my math worked pretty well for using something called a non-Hermitian matrix, which just means non-symmetric. So taking what I had learned from engines 22 and 23 and kind of breaking one of the rules that we had established in that class, but the math fit pretty well. But what I found was the math also told me that if you change some of the parameters, including the phase, you could have the system go unstable, which means it no longer follows linear dynamics, and you would go into the world of nonlinear dynamics. So Juan and I and you were in the lab, and we said, okay, well, there's two ways to make this system go unstable. One is to change the phase of this coupling loop to a very specific value, to pi, essentially. And the second, or kind of a combination of the two, is to increase the amount of gain on those amplifiers. So we combined those two together, changing the phase of that relationship and the gain between the two cavities. And we found that we could switch in and out of nonlinear behavior and unstable behavior. And I still remember the day that we were in lab and we had seen that we were getting signal on the spectrum analyzer without having any drive going in. So normally you drive the system, you basically probe it, and you look at how much of that drive you see on the output port. But we weren't putting anything into the system. We were just letting it run for free. And suddenly we see a super thin, narrow, high resolution, high fidelity peak in frequency around where we know the cavity is supposed to live in frequency. Yeah. And we're like, what did we just stumble across? Yeah. And it's
we could move it around with phase.
And we can move it around. And it's so interesting because when you learn about electrical engineering, you'll learn about the difference between a resonator and an oscillator. And an oscillator is, you take that same resonator I was talking about before. It could be like a resistor capacitor, inductor, or a mass spring damper, and you put it in feedback with itself. So you take its own energy out and you amplify it and feed it back into itself. And then you get a self-sustained oscillator, which is the basis of old radios, the basis of everybody has a self-sustained oscillator in their phone, which is just quartz naturally does that. You don't need an amplifier necessarily. And most of the best clocks in the world are based on oscillators. But we didn't expect to have an oscillator where instead of taking energy out of one resonator and feeding it back into itself, you're making this hybrid oscillator between two resonators instead. And the oscillator loop is this loop between them. I think that was the genuinely novel thing that we had looked at, and we were able to find all this oscillator physics and all this coupled resonator physics in one platform.
Yeah, I don't know. I don't like over claiming, but I don't think anyone's done that before. That specific type of coupling, like phase tunable, non-reciprocal. And I spent a lot of time, again, like from a quantum physics background. In my PhD, we built a lot of lattices, these like hyperbolic lattices. This renders these kind of structures. This is inlaid in wood. But, you know, all of these resonators are also oscillators. They're, you know, this is obviously shrunk down on a chip. But this is a hyperbolic lattice where it's sort of regular tilings of heptagons. So each sort of closed cycle has 7 sides, which is sort of not something that's easy to do in a plane for most things. And there, it was all about the coupling, like who is coupled to whom. But essentially in something like this, if everything is nice and symmetric, when you add interactions, it just sort of splits them apart in frequency. And, you know, essentially this phase knob that Alex was talking about sort of smoothly moves you from splitting modes apart in frequency. And this comes down to like the classic 2 masses, 3 springs. There's like this common mode, and then another mode that is a different frequency. When you add phase non-reciprocity, and like, you know, specifically when you make it sort of pi, you rotate, or I guess pi over 2, you rotate it in the complex plane, and then you get gain and loss, as Alex said. So now you have modes that are at the same place. One of them dies really aggressively and the other explodes. And if that growth rate is bigger than the total loss, then you get these limit cycles, which is totally bizarre from like a quantum physics background, I would say. Not so bizarre in electrical engineering, but as Alex said, kind of bizarre to have it sort of arising through coupling.
Yeah, exactly.
Amplified coupling.
And certainly bizarre to physicists. Point where we looped in a collaborator in the physics school because they saw this self-sustained mode between these resonators, and it was very intriguing to them because, I mean, limit cycles in general are just really, really cool. Yeah. How do you have a system that is self-sustaining a beating or an oscillation without any external drive? For example, your heart is a great example. Nothing is particularly pumping your heart. You know, your heart has a feedback loop that keeps it oscillating, but that feedback loop is interesting because it has a built-in regulation where if you change the power on it a little bit, or if you change the dynamics, that oscillation can grow momentarily, but it will slowly find its way back to a natural resting point. So it's really interesting how that works in the heart, for example, and it's really interesting how it works in our system. And you can have all these different phase changes between those limit cycles. And it was one thing that I thought was pretty cool with Juan was we went through the math of all the different ways that we could change the limit cycle or have the birth or the death of the limit cycle, and comparing that to different heart conditions. So, well, not like not in a weird way, but like, for example, there's this interesting heart condition called atrial fibrillation,
Hmm.
where it's not a heart attack. It's just that your heartbeat becomes aperiodic.
Hmm.
So it no longer has a well-defined frequency,
Hmm.
and it's called a chaotic attractor because you're not necessarily in like your heart's not beating super super fast, you're not having a heart attack, but it's an irregular heartbeat that doesn't
Hmm.
have a single frequency. And that's a chaos theory thing that can happen with your oscillators. I don't know if we had that happen with the cavity, but I know when we went to using yttrium iron garnet, which is a
Oh,
different type of resonator, we were able to see some chaotic behavior where all these crazy aperiodic frequency
hmm.
peaks would show up, and
Oh, yeah, yeah,
we were like, "Wow, that's atrial fibrillation of
yeah.
our yig."
Hmm. Yeah, so Juan worked with Lorenzo Viola and Michiel to build out the theory for that. And I think from there, I'll just back up, I guess, that at the time we were setting up the fridge to do sort of more traditional quantum computing types of things. But I was fortunate enough to get this DARPA Young Faculty Award, where you sort of pair up with somebody at DARPA. So I worked with Mukund Bengatolore, who was curious about sensing. And specifically, there was this idea of using exceptional points, which is a fancy name, but it's essentially places where modes start to coalesce. And from a mathematical standpoint, it's where eigenvalues and eigenvectors sort of combine together. It's where a lot of math kind of breaks. Um, which I think is a really interesting mathematical object, but people have been trying to use them for sensing. Um, sort of, it's been kind of hot in the last like what decade or so,
Yeah, yeah, it's been about a
and I
decade.
think the literature has been all over the place. And this is one of those things where I guess for the audience that is just kind of interested in science but hasn't done it, science is a moving object. Like, you do the best you can with science papers. You try to make sure everything's correct and consistent, but it's constantly evolving. And I think my program officer really wanted to get to the bottom of like, is this useful or not? Because like some groups would be like, oh, this is awesome. And some groups would be like, there's no way you can actually build a sensor out of this. And it was very hard to determine like who was kind of BSing and who was like actually honest and whether they were looking at the right things. And so basically I was lucky enough to get this grant early, um, because basically we pitched using these cavities and these tunable amplifiers and phase shifters to be able to like go directly, experimentally go directly to these exceptional points and just directly measure whether there's a sensing advantage. And the key sensing element was these yttrium iron garnet spheres, which, as Alex said, basically, long story short, they're this amazing material where there's a bunch of unpaired electrons, but really what they are is they're magnetic field tunable oscillators, or really magnetic field tunable resonators, and we can turn them into oscillators. So our goal was to use one of those as a cavity so we can tune that very precisely with magnetic field and then just sweep through these exceptional points and actually determine whether there's, say, a boost for magnetic field sensing. And I think that was like an important I want to get to the point where we saw like the peaks converging, and I think maybe I'll toss it back to you though, because I think this is one of those moments where like I'm really proud that we hit it from a very experimental angle. And maybe you can unpack like whether you agree with that, but especially like why that was useful.
Yeah, exactly. So we finished up this, where we were finishing up this project with the two cavities, and the idea was, okay, how can we take this architecture of tunable coupling and non-Hermitian, non-linear behavior, how can we build something potentially like applied and useful, like the sensing platform out of it? And so we found that all you had to change in the system was add frequency detuning between those two resonators, so they're not both at the same frequency together, and dissipation detuning. And this is where you get all into the non-symmetric, and basically nothing about those two resonators is the same anymore. We started with two identical cavities, and now we're at a microwave cavity and this black sphere that somehow changes its frequency with respect to external magnetic field, with a completely different loss rate, completely different frequency. So totally different between those two modes. Mm-hmm. And that difference, that breaking of that symmetry, allows you to gain access to these exotic non-Hermitian behavior, such as these exceptional points. And we had sort of just jumped right in to the experiment instead of starting with the math first. We were like, let's just build it and see what we can create. And I think that was a little difficult at the start because making a cavity and the yig look the same. I just talked about how they have different frequencies and how they have different dissipation rates, but you still need them to fundamentally both be resonators. If you take this little sphere, it's 1 millimeter in diameter, and you just plop it on the floor, it's not going to resonate. You have to do some extra engineering on top of that to turn it into a resonator. And I think the engineering behind all the different things that we tried, putting it on top of a waveguide, and then it would just suck up energy out of the system rather than acting like a resonator, took a long time to figure out. But I will say that eventually we had come across this paper that came out in 2023 out of MIT Lincoln Lab from John Barry and his co-authors. And they had this architecture that you could make a resonator or an oscillator out of yig. And so when that part was solved, we were off to the races for what does this actually look like? Mm-hmm. And what we found was that we would basically keep one of the peaks, one of the resonators in place. So keep it the same place in frequency, keep it the same place in dissipation rate. And you would take the yig because it's highly tunable. It's easy to change its frequency. You just change the magnetic field. And we found a way to easily change its effective dissipation rate. We just said, what if we just sweep this all around, sweep the yig all the way through the cavity, back and forth, change the phase, those kind of behavior. And we found what people reported with exceptional points, that if you did that very carefully and you chose particular parameter values, you could see that the yig and the cavity peaks split apart away from each other with a small change in magnetic field. They split in a massive fashion. Like the rate at which the peak splitting is with respect to the input magnetic field is a very high derivative. You can think of it as a slope of response that you're actually reading from the system with respect to the stimulus you're trying to measure, which is magnetic field, which fundamentally sets the part of what makes a sensor powerful. Is how much does the thing that you're reading out change when you have the thing you care about measuring change.
Mm-hmm. There was one thing I want to highlight, though, that in order to get the loss rates the same, because you mentioned frequency and loss rate, those are kind of like duals of each other. If you really want to get this nice response by tuning frequency, the loss rates have to be the same. And in order to do that, we just added feedback loops on each of the sites. So it's basically this tunable coupling architecture, but then feedback loops, and then we couple strongly to the yig. At that point, I was so proud when we had that, because it's essentially the most tunable dynamics solver you can build, because we have full control to an extent over frequencies, loss rates, coupling, including the phase of the coupling. And it ends up being that I think I love building stuff, and I think it's really cool that we had that kind of control. And we kind of had to see any of the physics that is in the paper that you can find in the link below. But I guess, from there, I think the story got murky for a bit because it's a subtle problem. But I mean, maybe walk us through what happened after we kind of got the setup dialed in.
Yeah, and really quickly, so those feedback loops, if you don't drive it super powerful, then instead of the system going nonlinear, you can just change the effective width of that resonator.
Yeah.
So as long as you're not going nonlinear, you can effectively change your dissipation rate, which is a really cool trick because you can do that digitally with these digital phase shifters, digital attenuators.
Mm-hmm.
And so I had built not only the physical hardware setup, but I had built an entire software platform and a graphical user interface
Mm-hmm.
where I could change all the parameters from my little cockpit triple monitor setup and just have the spectrum on one screen and all my controls on the other screen and like the math on the third screen.
Mm-hmm.
So with the hardware and the experimental platform and the software built, it was time to measure these exceptional points and see how the whole system works. And one thing that I'm particularly proud of that we had come up with was instead of only measuring the coupled system, so instead of just measuring the system while everything is turned on, we added switches in that coupling loop that we could turn on or off. And we added switches that could let us probe the cavity or the yig in isolation and the whole system coupled.
Mm-hmm.
And why that's important. That's important because if you blindly look at the coupled system and you look at those peaks, you can see that those peaks change with a square root behavior near an exceptional point or near an exceptional point because the peak locations are the eigenvalues of the system, right? I mean, when you look at a single resonator, if you basically what I'm saying here is when you're in undergraduate engineering, you learn about engineering systems through Laplace transforms and transfer functions and matrices, linear algebra, and state space. Those two formulations are exactly the same, but state space is a little easier once you get bigger systems that are coupled together with many modes. So the eigenvalues of the state matrix are the same as the poles of the transfer function denominator, basically just telling you the energies of your modes.
Mm-hmm.
So you see the peaks, and you assume that those are the eigenvalues. But because we had added this isolation system, we could not just guess what the math was. We could actually build up from first principles since we knew the individual frequencies at all times, where the eigenvalues versus the peaks actually are.
Mm-hmm.
And then what happened was you get these coalescence of the peaks. And I did the math. I was like, okay, here's where the eigenvalues are supposed to coalesce. Here's where the peaks are coalescing. And they're nowhere near each other. For some cases, they could be like a little bit away from each other, and you could say, experimental error. For other configurations, not even close.
Mm-hmm.
And it's really hard for me because looking on papers that were published online, if they
Papers that are still published after, like, this is still happening.
Papers that are still being published now, they will look at peaks that show up in transmission and they'll look at eigenvalues directly of the system that they can either measure or fit with mathematics and call that all the same thing. Mm-hmm. And the only reason we were able to come across this major discrepancy was because we said, let's not trust the coupled output as the only thing that we measure from the system. Let's isolate each resonator at the same time so we're getting triple the information as normal. And when you get triple the information, you find that the math doesn't line up. The eigenvalues are not.
And this is also, I would say, like, on that took modeling. We can get into like all sorts of really important. I think what is a good model is a very important like theme today because I don't know, gets into AI, which I think we should not go that route right now. But I feel like you, I would say in our lab kind of pioneered this MATLAB like symbolic math toolbox, and it allowed you to sort of build models that you could sort of validate that all of the math was correct. And I think I'm really proud of your open science initiative. Like all of the stuff Alex used in his paper is all very nicely organized on GitHub. And I think it's a model for like open science. or we are just an open book. And so I think, but there was a lot of nuance. So you build all these control knobs, and then you do fitting. And I think this is one of the driest subjects, but like uncertainty estimation when you do experiments is like so important. And I think we really hit it hard. Like you built all these really awesome GUIs and things that would just like do live fitting, and so you could propagate uncertainties through. And it wasn't until that machinery was working did you come up with this like, oh no, this is not like some just like squishy like hand wavy stuff. Like there's a discrepancy, you
Yeah.
know.
Yeah.
And
That could not be explained by the uncertainty in the fits, uncertainty in the experiment. There was no way that it was just a statistical artifact. It was something real.
yeah. And I think this also like what when I'm trying to explain this in layman's terms, essentially, and I apologize for those of you just listening, but essentially you have two sort of peaks in the spectrum. What we're looking at is these exceptional points where they come together and it becomes one peak. Now, on the one hand, that's really simple to kind of visualize. They kind of just come together like a square root, like whatever. They just kind of merge together. And the question is, how quickly do they merge as a function of whatever knob you're using to tune them? And as somebody that's looked at a lot of noisy peaks in my life, what we were staring at near the quote unquote exceptional point was two broad peaks, sometimes very broad peaks, merging together. And when they start to merge, there's this overlap region where it kind of bows up, and it's what you end up with is this like weird, broad, kind of flat peak.
Mm-hmm.
And at some point, when you're trying to fit, is there what I remember in the early days, we would do like, is there one peak or two peaks in like SciPy or whatever you're using, like before you built like the real model. And it would just like, it depends on what you ask it. Like you're fitting some data to either like, do I have one peak or two peaks? And you can fit any, like when they're close, it will be happy to fit one peak, and when they're close, it'll happy to fit two peaks, and you can't just use R squared to differentiate them. And I feel like there is a glut of papers that essentially are just naively fitting two peaks to what is by all practical considerations one peak.
Yeah.
And the error bars are massive, and they're saying, oh, this is awesome. And I think this is like kind of the core of like why this is super murky, and I think EPs are kind of a mess.
Yeah, no, 100%.
It's just bad science.
But fitting peaks is just really hard.
Yeah.
You don't have a first principles mathematical closed form solution.
Yeah.
Fitting peaks, especially trying to fit multiple peaks where you think that there's two or one, and figuring out exactly where that difference is really, really hard. And I went into a whole rabbit hole of different methods. One method is, instead of fitting the peak itself, you can try to take the derivative and then fit the like the critical points of the derivative. But if you have any sort of noise in your peak, then the derivative gets all these crazy spikes that mess up your solver. So then you're like, okay, well, what if you take the derivative and then smooth it? But then if you smooth it too aggressively, then you lose your peaks, and then you can have your peaks be depending on how much you're smoothing. And so you basically just get into this statistics mess where you can get any answer that you ask the solver for. And I think kind of the importance of starting from first principles and starting from just the fundamental mathematics of your problem. Basically, make as little assumptions as possible about your system, and then just use the machinery of mathematics to figure out a final model. And I think your model is good if it can both explain and predict your system. So
I actually, that's a great point. And wasn't until midway through this spring teaching 23, because some of the students don't love math as much as we do. And frankly, don't love physics as much as we do. Many of them do, for the record. But I love physics, and I love the ability to use math to describe the physical world. And that was enough for me. Like, but actually what I realized, and I was kind of thinking through like neural networks, which are universal function approximators, like, very useful for fitting anything, like quite literally. But the question is, what is the predictive power of that?
Yeah.
And math, like analytics, or even like a good numerical model, it's that predictive power that's why engineers should care about it, because it allows you to build things, right? It's not just like describing some weird obscure physics. It's saying this is a good model of this physical system. So now you have all of these parameters and you can tinker with them, and the system does something different. In our case, we can do sort of like crazy different system dynamics, right? And that's the power of the model. And I think you're modeling, I mean, at its core too, maybe it's only a matter of time before we talk about this, was it 1665 citation? So, I mean, what was the model specific, very high level? Like, I think that's a really fun story.
Yeah. So, and I just wanted to say one thing that, like, yeah, when you switch from math being just a fitting tool to math and experiment in a feedback loop with each other, where the experiment validates the math, then the math says, okay, well, if that's validated, what if you change this and we can get this cool exotic behavior? Well, if your model's good, if you do the experiment, you're going to see that weird exotic behavior. And then now you validate the math even more. And you just get this feedback loop where you can find all these really interesting systems. And sometimes it's actually so good that you can have a model that is decades ahead of any experiment that could do it. And you just end up being proven right in 50 years. Like Einstein coming up with black holes 50 years before black holes existed, because GR was such a good model that that feedback loop was tuned.
Yeah.
What was
also, dude, with what you were talking about with like people doing just like Lorentzian fits and like calling that the mode frequencies, I think at its core, dude, the problem is there was no tuning. You need experimental tuning that you can like rely on, and hopefully that doesn't mean like building a whole new thing where you're propagating a bunch of uncertainties. Ideally, you have nice control knobs. And I almost feel like what you really want is a fitting procedure where you like randomly select parameters of the physical model that you're probing directly. And then you extract in your mathematical, or like, your mathematical model, and sometimes predicts that. And you kind of need a self-consistent like platform more than you need like fitting of individual curves.
Exactly.
And I think that's something that didn't like, I don't know. I think there's a lot. And on the one hand, like a nice toy model is fine, but it wasn't enough for you. And
it wasn't enough. No, I was never going to get past the number of peaks changing, the derivative needing to smooth. And I was like, how am I going to publish something where it's not reproducible? Without a good fitting without a proper model, it becomes not reproducible, because depending on how many smoothing layers you do, or depending on pi settings, you can get completely different answers.
Yeah. So what was the conclusion? I think like it's sort of been like, we now build this thing where you have the mathematical model and you have this experimental platform, and you convince yourself that it was working.
Yeah.
But what did you find?
Well, so we went back, and instead of just looking at the eigenvalues of the matrix and treating that as the end all be all, we did some math to actually solve for the closed form transmission through the system, assuming that the eigenvalues and the transmission would have some sort of difference between them, whether or not that was the case. So we have this transmission model, and it is the ratio of like a polynomial to a fourth order polynomial. It is a complete mess. And I'm churning through this in MATLAB. And so I have this massive rational function that takes up this much space on the page. And then in order to find where the peaks are, I have to take the derivative of that function and set it equal to 0, and then solve for those locations. And so now you're taking a function that literally has this much space on your screen, taking the derivative, which is not that hard, setting it equal to 0, and then solving for all of the values that make that equal to 0 true.
Yeah.
Which you end up with a cubic equation, which makes sense because there's always 3 extrema. If you have 2 peaks, you have a valley between them, and you have 2 peaks. So you get a cubic. But the cubic took up 500 or something terms in my MATLAB window. 500 terms. So now the question is, okay, well, now I've got 2 evils here. I've either got to do this SciPy fitting and tell reviewers to use the exact same SciPy settings as I did, or I print out an entire page of LaTeX, which is just polynomial. So I was a little stuck here. And I was watching this YouTube video by Veritasium, who makes these they're incredibly animated and they're incredibly well produced. They're professional level quality, and they're great for getting popular science topics out into the wild.
We had both watched that recently.
Yeah, we had both watched, because I remember we had mentioned it in class, because it's a math topic. It's about how imaginary numbers were invented for the first time in order to solve particular problems, and how there were these math duels in history where if you were a professor, somebody could challenge you for your professor title by giving you a math problem that you can't solve. And back then in the Renaissance, people were very interested in solving cubic equations because quadratics had been solved by the Babylonians and they're not that hard. Cubics were a lot harder to solve. So there's this professor that gets a list of 30 cubics that they have to solve in order to keep their professorship job. There's no tenure back then, because if a student challenges you and they win, like, you're out. So this professor is like, I've got a month to solve 30 cubics. My job is on the line. And this ingenuity pops out where he comes up with this particular transformation that you can make on any cubic equation to make it a little bit simpler. It's called a depressed cubic transformation. And after watching that YouTube video, and by the way, after doing that depressed cubic transformation, the cubic becomes much easier to solve. The professor did it, solved all 30 problems, kept their job. And then didn't publish the depressed cubic method, because then if you publish it, somebody could use that in order to keep their job or part of questions.
We took a lot from that, but then also did explicitly the opposite by putting all of the math and like everything is open.
Exactly. The exact opposite, where I'm not trying to keep, that's not how you keep your job anymore. You do the opposite to keep your job by sharing science out with open world. Yeah. Exactly. So I decided to use that same transformation on my massive cubic that took up 500 lines and would have written an entire LaTeX page to do. And then suddenly, after that transformation, the entire cubic shrinks down to this beautiful equation that you can read on one line. It fits in the research paper. It's like a
let's see,
one of the first 10 equations.
5 or 6.
It should be the first equation in transmission spectrum analysis.
Oh yeah, 10 or 11.
And suddenly I have an equation that I can write down on a piece of paper. And then from there, I was able to incorporate that into the fitting model, and the match between the theory and the data was really, really good.
And then we got all these very clean, like, merging of peaks that look gorgeous. But what did you end up finding? Like, what are your thoughts on, I mean, I don't want it to be overly technical, but Alex found these, like, transmission peak degeneracies is sort of the right framework for this. And we found a few of these sort of transmission peak degeneracies, which are like what everyone used to think every EP was. It's like EPs, but in the real life. Some of them have nice properties, but I think the conclusion is sort of that the vast majority of them are useless, right?
Yeah, well, so it was. We were not the first people to coin the term or to find this discrepancy between EPs and TPDs. But we wanted to unify the mathematics for both and extend it using our platform where we have this phase tunability. The previous papers that had done TPDs could only look at one TPD at a time. And we wanted to figure out what is the entire possible family of two-dimensional TPDs and what are their properties. And yeah, unfortunately, in finding the properties of every two-dimensional TPD, we found that most of them, almost all of them, have this unfortunate property where their sensitivity to what you're trying to measure is boosted, good, but the sensitivity to what you're not trying to measure is also boosted as well, pretty much by an equal amount. And in some cases, it's worse in the direction that you don't want to measure. It actually was so bad that there were two TPD papers where, like previously published, where one paper, they were using essentially the same type of transmission peak degeneracy. One paper was measuring in the sensing direction, and the other paper was measuring in the opposite direction. And they were both claiming a sensitivity enhancement. It's like, wait a second, this paper is measuring the noise of the other paper, and this paper is measuring the signal of the other paper. How can you both be claiming a sensitivity improvement if you're measuring each other's noise?
Yeah.
But there is a silver
and they
line.
probably put tons of lipstick on those papers and shoved them into fancy journals that just so the point is that you should do good science, I think. And the point is that you kind of need this tight connection between a really good experimental platform that you trust and a really good mathematical model that's exactly trying to model your experiment. Because if all we did was eigenvalues, we would miss all of this. But if you really want a mathematical model to describe what our measurements are, that's the only way you get insights like we've established, which is like this, that you've set up this whole mathematical framework. So I think it took a long time because I applaud you for, your patience to just do this right. It's kind of funny, this DARPA program is over, and it's kind of a funny end that it's the first time in my career where we've done a project and it ended up just kind of killing the next. Like usually you do a project and then it's like, oh, this is a great result. And then you do some minor tweak on that thing and then you get another paper. Here we're like, well, I think we killed most of this field. Maybe. I mean, there's still a lot of interest.
There's a little bit of a silver lining. Yeah. I'd say what was, like we were talking before, what makes a good model? What makes a good model is not only that now I had math to fit my data, but also now we had a predictive tool. Mm-hmm. And I think that was sort of the silver linings that we included in the paper. Was we had a mathematical function that could tell you how much sensitivity you're getting in the signal direction, how much noise you're getting in the opposite direction. And instead of testing every possible combination on the experiment, which is impossible, you can solve for there a location in parameter space that you would never guess on your own, because it's 1 point in a million, a needle in a haystack. Is there a choice of parameters that can help you and mitigate some of that noise? And what's really cool, I think one of my favorite figures in the paper is figure 5. We show that you can describe the mathematics of the system using this really funky math concept called a cusp catastrophe. And we essentially just said, what if we solve for where that funky cusp catastrophe disappears? Like, we don't want it there because it was adding to the noise. What if we just tried to remove that? And we had an equation for the cusp. And if you have an equation, you can figure out where it disappears without having to test every single possible output. and we constructed a set of parameters where that cusp catastrophe disappears, but you still have your transmission peak degeneracy. And that is the only place in parameter space for 2 dimensions where you have a much stronger chance of actually using one of these transmission peak degeneracies for sensing. Yeah. It's still not a perfect candidate, but
it's the best you can do.
Provably the best you can do in 2 dimensions.
Yeah, which is an awesome outcome. I think that's really, like, what more can you ask? I'm excited to see. I hope people actually read this paper, because, yeah, it ought to be the framework by which people kind of like tune their setups. Because what it sort of means is if you're not actually deliberately engineering your setup to be right in the money, and there's a lot of things that you can tune, then you're host. Like, then sure, you see some fancy thing and you can do shady fitting, and try to shove a paper through a view by using a bunch of fancy words, and that's just not science I want to be a part of. So I'm really proud of what you did with this paper. I think it was a long journey, but it's very satisfying to see it end to end. And we have lots of other stuff coming out related to these ideas and sort of building on the architecture. But I do really like this idea of like model and experiment, and I think it is a really good model of like what good science is and what the power of a model, because it gives you an amazing amount of predictive power, and it allows you to kind of sniff things out. And I think it's not, a lot of people don't think about models. You're like, oh, this is the physics. And it's kind of like, well, so like, how could you discover new physics, right? On the one hand, yeah, you could like sort of take theory and try to keep doing more math. But on the other hand, it's like you have the best model you could possibly have, and then you do an experiment that doesn't agree with that model, and you like convince yourself that that experiment, these are all the parameters of your experimental apparatus, and you've controlled all your unknowns, and then you do an experiment and it like deviates strongly from the model, right? And then you adjust. Like, this is such basic part of science, but yeah, I think this project really kind of like cuts to that idea really deeply. I don't know, but
yeah, no, I agree. It's and I think one thing that I learned from this paper that I would love for everybody reading it to take away is extract as much information from your experimental apparatus as you possibly can.
Yeah.
Why would you only measure the coupled output if you can, like, the fact putting the switches into the system so that we could cut off the coupling and in real time measure what both resonators are doing individually and what they're doing coupled.
Yeah.
It literally gave us triple the information out of our setup. And I don't think I would have been able to come up with this entire premise of the paper, the transmission peaks versus the eigenvalues, if I didn't have that information. So don't leave any information out of your experimental apparatus on the table. Extract everything you can.
Yeah. Actually, there's a propagation of those things, because that rich data set allowed you to build this mathematical model. And then the mathematical model is kind of the end product of this that we validated, right? But then once that mathematical model is like sound and we've convinced ourselves that describes the physics, then you can find these special points.
Yeah.
But if you just search for these special points in a mathematical model that doesn't apply to your experiment, no offense to my theorist friends, but like, who cares? Like, I don't know. Physics is an experimental science. And math is an incredibly useful tool to, again, going back to like this realization I had, it's not just a useful tool for describing like a given set of dynamics. It's a model for saying that physics should apply even if you change these parameters. And I think your model does that so beautifully. It directly predicts what the experiment will do in all of the minutia,
Yeah.
but also
Even
in a deep mathematical elegance that the combination of the two is extremely powerful.
even if it's completely counterintuitive as well. So one of my favorite results in the paper, even though it's not, it's not particularly groundbreaking, but I really like it because it was purely predictive power, was nobody had looked at phi equals pi over 2 TPDs before. People have looked at EPs a couple of years back for different phases, but nobody had ever looked at a phi equals pi over 2 TPD. And we found that as you rotate the plane, you rotate the EPs exactly the same way. And at phi equals 0 and phi equals pi, you look at a straight line that cuts between those two EPs, and you basically follow that line, and that's your experimental protocol. So when you go to phi equals pi over 2 and you have the two EPs at like a 45-degree angle from each other, you would intuitively say, let's draw a straight line between them and follow that straight line, and we'll see the phi equals pi over 2 TPD. And everybody would guess that, because why wouldn't you? Well, it turns out if you do the math, actually the only path that you can take to see it is this weird hyperbola, which is like a shape maybe like from like geometry class. You have to follow with an experimental apparatus a hyperbola with a very specific equation, and that's the only way to see a phi equals pi over 2 TPD. And so I looked at that and I was like, that's not a straight line. That's way more complicated. But what's crazy, and not only is it more complicated, but it is literally impossible to come to that conclusion without the math.
Yeah.
The intuitive conclusion is draw a straight line. You could have never come up with that hyperbola otherwise.
And again, I think you could do that cut and you would get some janky splitting.
Yeah.
And somebody would fit that to a stupid model, right? Like this is what happens if you're just naive. Like,
exactly.
Keep going.
So don't follow the intuition, because the intuition can break. So then we built a control system that would tune the parameters, not just in straight lines like we were doing before, but tune them in a hyperbolic trajectory. And I remember getting the control system to work, and it was following all these. I could define any shape in parameter space, and the experiment would follow that. And I was like, okay, here goes nothing. Let me plug in this random hyperbolic equation that the math is telling me is going to come up with a new TPD, and let's just see what happens. And I remember, because I was running an overnight. And I remember like waking up the next day and seeing this beautiful square root that looked exactly like a TPD. And I was like, I love that. I just love that. I can't believe that happened.
Yeah. But that's also a testament to your engineering of that setup, which like building that infrastructure, the mathematical infrastructure, but also the experimental infrastructure. And I'll just say this now, because I don't want, like, we need to make sure that when you graduate that we pass that along somehow, because there's a lot of wonderful like stuff that you built for that system that you could automate that. Like that's kind of a crazy thing to do, because it's tuning parameters, it's I think feedback on some of those parameters, it's doing fits, like there's a lot in that, and I think that's really cool. I think it sort of speaks to, I mean, my lab philosophy, but also like, you did much of this project on your own, and I think one of my first projects in grad school was mostly my own, and similarly, like it takes a while, but I think there's a certain level of pride that you get when you kind of have seen a project from start to finish like this. And yeah, congrats on getting to this point. And yeah, it's been a blast talking to you. I had said let's do an hour, but I think we kind of went over just because there's a lot to unpack. And I'm really excited about this work. I hope people read the paper. Should reach out if you have questions about it. I guess, Alex, in closing, I don't know, there's always like some podcast kind of like hook thing. Either like, I guess one of the ones I like is like, what are you reading? But usually that should be something to prep before the podcast. So I think a good end for this podcast is kind of like, what excites you? I mean, without giving away too much, but like, what's the most exciting thing that you see sort of on the technological frontier, or like things you want to build that you're excited about?
Yeah, I mean, we could do you could do an entire episode on AI
Yeah.
and LLMs, but I think uh LLMs and useful LLMs, so like actual like agentic coding tools
Mm-hmm.
and stuff like that, not just like chat bots or
Yeah.
video generation that I think that's a lot of that's junk, but I
Yeah.
think the AI that actually integrates directly into PowerPoint or LaTeX or Word or your coding terminal, or can, integrate into your experimental systems directly.
Yeah.
It is such a democratization of resources.
Mm-hmm.
What I mean by that is, before AI, if
Assuming you can pay for it.
well, you're right. Yeah, you do have to pay for it, but 300, it's a lot of money per month, but it's a lot cheaper than the amount of, like, basically what I want to say here is, if I went back, if you offered me two choices to build a company or build research, and the two choices were, 5 years ago, I'll give you $1 million,
Mm-hmm.
or today, I'll give you unlimited access to the newest and greatest AI tools to build a company, build a lab, build a startup, whatever, I would choose the AI tools. It is absolutely, because
Well, it depends on what company you want to run, right?
yeah, if you have
Certainly
anything
software.
software, if there's anything that can be digitally controlled, whether it's pure software or software mainly handling like a lot of your experimental stuff. Yeah, if you're going to build like a robotics company, I need the money.
Yeah. Or a
But
quantum computing company.
or a quantum computing company. But if you're doing something that the and maybe in the future we'll have some sort of physical AI, and the question will be the
Yeah.
same. But
Well, I
for
think you're like sort of, I mean, going back to this like hyperbolic sweep thing that you talked about. Those kind of things, like you can help have an agent on top of that layer
yeah.
and help backstop things. And like, I've had lots of overnights where the code like crashes and you just don't get any more data. And to have like a backstop that saves you a ton of time.
Yeah.
So I totally agree with you. I might still take the $1 million, but I see where your point is. If anyone wants to give us $1 million, feel free. And the tools, we already have the tools, so we'll take the $1 million. But anyway, Alex, really congratulations for getting this paper across the line, and hope everyone listening gets a chance to read it or chat with us. So anyway,
Yeah.
talk
It was
to you
great.
later.
Thanks a lot.
Bye.